The strangest thing about space is not its vastness, but the fact that to notice it we need something that makes it vibrate. A ray of light crossing it, a comet slicing through it, your gaze seeking a direction. If we remove these signals, what remains is a silence we cannot describe, because even the word void evokes a container waiting to be filled. Yet, from this very ambiguity was born one of the most fascinating questions in physics. Does space exist by itself, or is it the result of what it contains? Is it a stage built before the play begins, or does it arise only when the actors step on it? For centuries, the dispute was mostly philosophical. The idea of absolute space, like an invisible grid on which things rest, is powerful because it offers security. I can say where I am even if everything else changes. Isaac Newton adopted it to explain the motion of planets and apples with the same formula. Behind that order lay a fixed, homogeneous, immutable arena. Gottfried Leibniz overturned the table. Without objects there is nothing to measure, and talking about space without relations is like talking about left without right, a mere linguistic game. Immanuel Kant, in his own way, moved the issue into the architecture of the mind. Space is a necessary form of sensory intuition, the way we organize phenomena in order to think them. 3 visions, 3 frames. But at some point, physics demanded more: measurements, equations, predictions. The leap came when space stopped being a backdrop and acquired physical properties. General relativity, completed in 1915, does not simply say that gravity is, as if, space were curved. It states that space, together with time, has a dynamic geometry that responds to the presence of mass and energy. It is an idea as elegant as it is demanding. The straight trajectories of objects are not straight lines in the Euclidean sense. They are geodesics of a geometry that bends. A planet does not feel a force pulling it. It follows the most natural path within an elastic floor. This can be measured. The precession of Mercury's perihelion, the deflection of starlight observed during an eclipse, gravitational redshift, gravitational waves recorded a century later by interferometers capable of detecting length variations smaller than the diameter of a proton. It is difficult to reconcile these results with the idea of a rigid, indifferent container. Yet this dynamic vision does not eliminate the logical possibility of an empty space. The equations of relativity admit solutions even in the absence of matter. Minkowski spacetime is the flat geometry in which special relativity works perfectly. It is an ideal limit, like a perfectly stretched canvas. But the real universe, observed on large scales, is not flat to the millimeter. It expands, and on cosmic scales matter, dark energy, radiation, and evolving structures determine its fate. More than asking whether space can exist without matter, it becomes interesting to ask whether that empty state has physical meaning or is merely a mathematical artifact useful for constructing theories. Here quantum mechanics enters the stage, with its intolerance for absolute nothingness. In quantum formalism, the vacuum is not a desert. It is the state of minimum energy of a field, brimming with fluctuations. This is no metaphor. Phenomena such as the Casimir effect reveal measurable forces that arise when the ways in which fields can oscillate between very close surfaces are restricted. Particles do not literally pop out of nothing and vanish like will-o'-the-wisps. It is more accurate to say that quantum fields have a structure that makes a dance of transient excitations inevitable, subtle effects that can be observed. In quantum field theory, what we call a particle is a quantization of the very field that permeates space. But then a deep coherence problem arises. If gravity is the dynamics of geometry and quantum theory describes everything else, what happens when we try to quantize geometry itself? Several research paths open from here. One, called loop quantum gravity, takes seriously the background independence of general relativity. It does not assume a pre-existing geometric space to feed into quantum theory but lets the very notion of space emerge from discrete elements, grains, of area and volume. In this view, space is not a substance but a web of relations. Tiny loops of information, spins, connected in graphs whose weave, at extremely small scales, replaces the continuity of classical geometry. This is not just theoretical poetry. The granularity predicts minimal values for surfaces and volumes, and near classical singularities such as the center of a black hole or the cosmological beginning. Gravity's behavior changes, avoiding the infinities that signal the breakdown of classical equations. In other approaches, such as those inspired by holographic correspondence, the geometry of a space can be equivalent to the quantum relations, entanglement, of a non-gravitational system on a boundary. A radical way of saying that space is not fundamental, but arises from the connections of something deeper. Regardless of the approach, a common thread runs through many modern ideas. Space might be emergent. If so, it makes no sense to think of it as a container waiting for occupants. It would rather be the result of the warp of physical relations. When we measure a distance, we are really probing how fields and matter interact along a path. When we speak of directions, we are reading broken or preserved symmetries. When we send a laser through an interferometer, we are watching space respond. It is a shift in perspective that echoes Leibniz's intuition but moves it into a quantitative territory where probability amplitudes, operators, and spectra of areas matter. This vision does not erase the explanatory power of general relativity, which remains an extraordinarily precise theory at all scales accessible to direct observation. At large distances, curvature explains orbits, gravitational lenses, and the cosmic web. At small distances, for now, the world is successfully governed by quantum field physics. The problem lies in the interregnum, regions of extreme curvature and minute size where the two descriptions must speak to each other. It is there that the question is decided, whether the vacuum is truly something, or whether space is merely the collective name we give to a statistical web of relations. A good metaphor is not enough to choose between these possibilities. We need verifiable predictions. Now imagine a thought experiment less vague than an empty room. Suppose you could switch off, one by one, all field excitations. No photons, no electrons, no bosons, no fermions. The equations would remain. If gravity is classical, you can still choose a vacuum solution, flat spacetime. If gravity is quantum, it may no longer make sense to speak of geometry without a state of the gravitational field. In some pictures, the ground state of that field bears no resemblance to a continuous space. It is more like a cloud of correlations that, with many degrees of freedom, becomes a smooth geometry, like the surface of water that, seen from afar, hides the granularity of its molecules. It is not easy to see this level. Physicists look for indirect clues, such as corrections to the propagation of gravitational waves, minute discrepancies in cosmological spectra, or faint signatures of a quantum bounce in place of the classical Big Bang. Until those clues become clear, we must keep several maps open. There is another intuition, often invoked but delicate, Mach's principle. The inertia of a body, in this view, is not an isolated intrinsic property but reflects its relationship with the entire content of the universe. If this principle were carried out completely, the very idea of absolute motion would lose meaning without the rest of the cosmos. General relativity seems to honor Mach only partially, and it is here that one sees how slippery it is to distinguish container from content. Defining space without reference to the rest of matter is not only difficult, it is ambiguous. It is no wonder that under certain conditions, even conceptually, to speak of distances already presupposes a physical system capable of measuring them. At this point, the initial paradox reverses. Asking whether space would survive the disappearance of matter is equivalent to asking whether the laws we use to define it make sense without their object. It is like asking whether temperature exists in a single atom. The concept is not wrong, but it becomes meaningless because temperature is an emergent property of many atoms. Perhaps space is like that. A collective quantity, well defined when countless degrees of freedom cooperate, evanescent when we try to isolate everything. If this intuition is correct, then the vacuum is not empty, it is a minimum of organization. And if we struggle to conceive it, it is only because we are used to moving on a stage already set, not in the rehearsal room where the technicians build the scene. So far we have looked at space as a dynamic structure, as a quantum emergence, as a web of relations. One piece is still missing. Understanding how this entity we seem to see with our eyes and measure with our meters intertwines with the time we count in seconds. We know they form spacetime together, but in what sense can such different quantities coexist in the same equation? To answer, we must find the precise point at which the illusion of difference arises, the mechanism by which nature unites what our intuition separates, and follow the thread to its most extreme consequences, without yet closing the discussion. The trail begins with a conceptual experiment as simple as it is decisive. Take with you two identical clocks and an ideal ruler. Let a ray of light travel from one end of the ruler to the other and measure how long it takes. If you repeat the experiment while moving relative to the ruler, you will discover that to keep the speed of light constant you must accept that the measures of time and length adjust themselves. From this arises special relativity and, with it, the idea that meters and seconds are not independent building blocks but coordinates of a single structure. Spacetime is the mathematical fusion that accounts for the fact that events distant in space may be closer than events separated in time, depending on the path connecting them. The straight line in this world is no longer where the distance is minimal, but where the spacetime interval is extremal, according to a metric of mixed sign. There is no mystery in the mingling of units. One simply introduces a conversion constant, the speed of light, which translates seconds into meters just as an exchange rate converts euros into dollars. When gravity enters the scene, this metric ceases to be universal and bends according to the energy present. Time flows differently near large masses, lengths stretch or contract depending on curvature, light paths curve. Yet the idea of an interval, blending meters and seconds remains the guiding thread. That is why the units are not an obstacle but a clue. Nature is telling us that time and space are not separate ingredients, but faces of one and the same quantity. In many modern equations, natural units are used in which the speed of light equals 1 and Planck's constant equals 1. In those units, speaking of meters or seconds is merely a matter of convenience. The true physical content lies in the geometry of the interval and the dynamics that shape it. The next step is to ask where this geometry comes from when we push it into the quantum regime. If space can emerge from entanglement or spin networks, what does time become? In some approaches, the most radical answer is that, fundamental, time might not exist at all. What we call time would be an effective parameter that appears when we observe a subsystem in relation to the rest. In other frameworks, time remains but is linked to clock variables internal to the physical system. It is a treacherous territory because it risks undermining our notion of cause and effect. Yet useful analogies exist. In thermodynamics, temperature emerges from microscopic degrees of freedom without any fundamental thermometer. In quantum information, temporal order can arise from correlations. If the strength of connections determines distance, then the change in those connections could define a before and after. These ideas are speculative, but not gratuitous. They stem from the need to resolve real paradoxes. Classical singularities, for instance, are not places in the cosmos. They are the way equations tell us we have pushed an effective theory too far. If geometry is quantized, those singularities could dissolve into phase transitions of the same network that underlies reality, replacing nonsensical points with highly correlated states. Similarly, black hole entropy, which scales with the area of the horizon rather than its volume, suggests that physical information is counted on surfaces as in a hologram, a powerful hint that links the amount of available space not to how much is inside but to how the boundary is stitched. It is as if nature were whispering that the spaciousness of space is an accounting effect of relations on the edge. This also helps us better understand why the idea of empty space is so slippery. In field theory, even the ground state is defined relative to symmetries and constraints. Change the background, and you change the vacuum. In an expanding cosmos, moreover, the definition of a particle depends on the observer. What is a vacuum for one may be a thermal bath for another, as shown by the Unruh effect for an accelerated observer. If the notion of absence of particles is not absolute, then that of geometric vacuum is even less so. The attempt to define space in the absence of everything runs up against the reality that physical definitions are operational. They depend on how we measure. Without matter, without fields, without observers, without interactions, without rules to compare clocks and rulers, what could it mean to say, here, or there, before, or after? This does not make it pointless to ask, what remains, when we remove everything? On the contrary, it makes the question more precise. What remains are symmetries and laws, that is, mathematical structures that, without physical realization, are only potentialities. In the language of physics, the container is never fully separate from the content. To speak of space is to speak of the degrees of freedom that can occupy certain states and of the transformations that relate them. In this sense, the idea that objects constitute space is not a naive metaphor but a rigorous ontological statement. The sum of possible relations is what we call space. Their evolution is what we call time. Remove the relations, and you remove space. Leave a lattice of possibilities, and you have the embryo of a geometry that, seen from afar, appears as a continuous fabric. If we return to the original image of the isolated room in the void, we can now reread it with a more discerning eye. What deceives us into seeing is the cognitive grid with which we organize the visual field: walls, corners, depth. But the physical definition of space does not rest on walls. It rests on the rules that govern the propagation of signals, the simultaneity of events, the measurability of distances through operational procedures. If the walls disappeared, those rules would remain only if there were still physical systems to realize them. Without them, space becomes a name in search of a referent. In this sense, the classical view of an absolute container is convenient but probably misleading. The emergentist view is conceptually more parsimonious. It postulates no more entities than are necessary. There remains one last knot to untie, and it is here that meters and seconds cease to seem alien to one another. Their unification is not a theoretical whim but the natural consequence once we accept that the speed of light is a universal constant and that gravity deforms the very metric. A unit of time can be converted into a unit of length by multiplying by c. A unit of mass becomes a length using Planck's constant and c. There exists a triad of fundamentals, c, h, g, that suggests natural scales where geometry, quantization, and gravity meet. At the Planck scale, the distinctions between space, time, energy, and information may dissolve into a single grammar. To say that space and time form one entity does not mean mixing apples and oranges. It means recognizing that both are fruits of the same tree. The question, then, is no longer, how can they unite, but why did we ever separate them? If the science of the past centuries has taught us anything, it is that the categories through which we think about the world are tools, not dogmas. Space as container was a powerful tool for building classical mechanics. Space as dynamic geometry accounted for gravity. Space as an emergent web of correlations may be the tool needed to cross the threshold where quantum theory and gravity shake hands. In each of these transitions, meters and seconds have adapted to the task, merging into an ever more coherent description. What we once called vacuum has filled with structure. What we called an object has become a field excitation. What we called a force has turned into curvature. What we called space may turn out to be relation. And yet, not everything is resolved. Burning questions remain. Does the energy of the vacuum truly match the value we observe as the cosmological constant? Does the granularity of space leave observable traces in the most extreme astrophysical signals? Is entanglement alone sufficient to stitch together generic geometries, or is something more required? Each answer brings physics closer to a point where the words space and time will no longer serve us as nouns but as verbs: to space, to temporalize, to relate. Until then, we can confidently use the language that works, knowing that beneath the smooth surface of the standard world, a subtler architecture stirs. And this is where the question that sparked this exploration returns. If we measure space in meters and time in seconds, how can they truly unite into a single entity? The answer is that they unite because nature forces us to measure events, not containers. And events are organized according to a metric that transforms meters into seconds and seconds into meters with the same naturalness with which we transpose a melody into another key. The deep unity is not a trick of conversion but a principle of coherence. The same reality that bends the paths of light demands that time slow where space curves, and that what we call distance be inseparable from what we call duration. And it is within this coherence that space, far from being an empty shell, reveals its true nature. Not a place where things happen, but the way in which things happen. If you've made it this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.